Good morning. Today is Unit 12, Day 10, Wednesday, April 15th, 2020. Just realized how sick of my voice you must be because I'm sick of my voice at this point. Yesterday you completed a quiz, hopefully yesterday, maybe you're working on it today, on kinetics. It is due tonight, Wednesday by midnight. So please make sure you finish the kinetics quiz, which is the first half of your unit. Today we're going to start the second half of the unit, which is on equilibrium. So you're going to need your Unit 12 note packet out once again to page 10 this time. So this is part 2 of our unit. When you are done, you're going to complete Unit 12, Day 10 skill check, which is Intro to Equilibrium, which will be due tomorrow, Wednesday by 11:59 p.m. Hey, look, it's me. I'm watching a scrap of plastic blow by across the street. That's how much fun I'm having. Hope you're having just as much fun too. All right, so let's get going. As I said, page 10 in your notes, we're going to start talking about equilibrium. Now, you got to be a little bit careful with equilibrium because every time people see the word equilibrium, they automatically see equal and they think, oh, that means everything must be equal, which is not necessarily the case. So we're going to go through and define equilibrium and what it actually means, and then go into some specific examples of an equilibrium. So the definition of an equilibrium is when the rate of the forward reaction. Now, what do I mean by forward reaction? A forward reaction means that your reactants are turning into products. So we represent that with an arrow pointing to the right. That is a forward reaction. So when the rate of the forward reaction is equal to the rate of the reverse reaction, which would be an arrow pointing to the left, where the products reform reactants. So you want to remember RE, rates are equal. That's what it stands for, RE. So in an equilibrium, the rate of the forward reaction, your reactants going to products, is equal to the rate of the reverse reaction, the products reforming reactants. So it's kind of like a cycle. Another part of equilibrium is that the concentration, the amounts of reactants and products in an equilibrium are constant. They are not equal. That's the big mistake people make. Concentrations of reactants and products are constant. So just like you want to remember RE for rates are equal, you want to remember CC. Concentrations are constant. Those are the two main parts of equilibrium. Remember, this does not mean the quantities of reactants or products are equal. So equilibrium does not mean your reactants and products are equal. It means the rates are equal. So you can kind of see this in a graphical form. Down on my x-axis, I have time, and then I have rate. So notice at this point right here, the rates are equal to one another. So I think we did RE, rates are equal. In your second graph, you have time and amount, or concentration. Notice these aren't equal to each other at the point of equilibrium. They are constant. The lines are flat. So CC, concentrations are constant, rates are equal. So you want to remember those two things for the definition. Okay, when we're dealing with equilibrium, we're going to be talking about a reversible reaction. Now, a reversible reaction, or an equilibrium, is represented by a double arrow to show both the forward, right? The forward reaction is this, and the reverse are occurring. So if you look at this example right here, we have a forward reaction and a reverse reaction. That represents an equilibrium or a reversible reaction. And what it means to say reversible is that my products, what I end up with, can regenerate the original reactants. So when I say the word reversible, I mean that my products, so in this case B and C, can reform the reactant A. And then A can form B and C. And then it can go in reverse. Unlike this reaction down here, this reaction only has one arrow. What this means is that reactants A and B form product D. but there's no reverse. D cannot form A and B. So this is only a forward reaction. Only a forward reaction. We're going to be seeing a lot of double-sided arrows like this. Sometimes I'm going to write the arrow like that. I don't write the full arrows, I kind of write half arrows, but they mean the same thing. Now you want to remember that equilibrium is dynamic. You're going to see that a lot. You're going to see the word dynamic equilibrium. Now what the heck does that mean? Equilibrium is dynamic, meaning it is constantly changing or fluctuating based on the conditions around it. So it doesn't just stay static. It changes if the concentrations of things change or the temperature or the pressure. It's constantly fluctuating. And we're going to see that tomorrow when we get into what is known as Le Chatelier's principle. But this is kind of just a basic overview of what I mean by equilibrium. Now, the next thing we're going to talk about is on page 11, and that is types of equilibrium. And we're going to use a flow chart for this. So, types of equilibrium. What's really important to know about all of these types of equilibrium is they all occur in a closed system. Unless the system is closed, meaning there's a top on it or nothing can come in or come out, it won't be at equilibrium. So notice all of these occur in a closed system. So in order for equilibrium to occur, it's got to be a closed system. Okay. So we're going to start on the left-hand side with a physical equilibrium, and then we'll get into chemical. Physical equilibrium, just like a physical change, involves just the change of appearance. So it involves physical changes. So a physical equilibrium involves physical changes. And there's two types of physical equilibrium. There's a phase equilibrium and a solution equilibrium. And the names kind of spell it out for you. So we'll start with the phase. A phase equilibrium occurs during a phase change. So a phase equilibrium occurs during a phase change. So evaporation or freezing or melting, that is a phase equilibrium. So I'm going to give you kind of two examples. I'll write one in here. Let's say I have H2O solid. I'm going to draw my double-sided arrow, my reversible arrow, H2O liquid. Now what this means is that the rate of melting, the rate at which my solid forms a liquid, is equal to the rate at which that liquid reforms a solid. That's why it's reversible. It can go in both directions. And remember, at an equilibrium, RE, rates are equal. So the rate of melting, going from a solid to a liquid, is equal to the rate of freezing, going from a liquid to a solid. And for water, this occurs at 0 degrees Celsius. So at 0 degrees Celsius for water. Notice this is a phase equilibrium. We have the same substance, H2O, it's just undergoing a phase change. Take a look at this flask down here. Notice I have a stopper on top. This is showing that this is under a closed system. Now this is representing a liquid. I'm going to say for the sake of this, it's water again. So I have liquid water, and it is, double-sided arrow, forming into a gas. Right? Notice it's a reversible reaction. The rate at which the liquid forms a gas, or the rate at which it evaporates, is equal to the rate at which it condenses or turns back into a liquid. Notice I'm not saying the amount of liquid and the amount of gas are equal, because remember, concentrations are constant. It's the rates that are equal. So I'm going to write rate of evaporation equals the rate at which we condense. And for water, remember, this is at 100 degrees Celsius for water. Good. That represents a phase equilibrium. It occurs during a phase change. Let's go back up to our second type of physical equilibrium, which is known as a solution equilibrium. Remember, a solution is when you dissolve one substance in another. And if that solution is, or excuse me, if that solvent is water, we call it an aqueous solution. So a solution equilibrium occurs at a solution's saturation point. So going back to unit 9 or 10, I don't even remember anymore. Now, what do I mean by saturation point? When something is saturated, we mean that the max amount of solute is dissolved. So it starts to pile up on the bottom. That's what I mean by saturated point. So when the max amount of solute is dissolved, we're at our saturation point, and we would say that we are at a solution equilibrium. So I'm going to kind of draw a picture down here. So I've got NaCl, sodium chloride solid, double-sided arrow, sodium chloride AQ dissolved in water. So how I kind of represent a solution equilibrium is that the rate that this solid is dissolving into the solution is the same at which that dissolved solution is reforming the solid. So the rate of dissolving equals the rate of recrystallizing. And I do have like this really lame video. Let's see if I can find it. I don't even think there's volume to it or anything. So you can kind of see the solution equilibrium, if I pull this screen up, happening. Ooh, he's talking. You can see that the chlorine is being removed at the same rate at which the sodium is being brought back, meaning recrystallizing. So you can see, wow, this guy's voice is thrilling. So we've got recrystallization, which is when it reforms the solid, happening at the same rate, oh, there it goes, at which it's being removed or dissolving. That's what I mean by solution equilibrium. Okay, and you can kind of see that picture down here. They zoom up on salt water, showing that the rate at which the salt is leaving in dissolving is happening at the same rate at which it's reforming the solid. All right, so those are both physical equilibrium. We're not forming anything new. They're just changing either phase or it's being dissolved in solution at the saturation point. What we're going to be dealing with a lot in this unit is chemical equilibrium. As we said from yesterday, the rate of the forward reaction is equal to the rate of the reverse reaction when we're at a equilibrium, which means that the rate that bonds are broken, so the rate at which bonds are broken is equal to the rate at which bonds are being formed. So I'm going to give you an example of a chemical equilibrium. So I've got nitrogen plus 3 moles of hydrogen, double-sided arrow, meaning reversible reaction, yielding 2 moles of NH3. Notice this is a chemical change because I start with nitrogen and hydrogen, and I get ammonia, which is completely new. So this is a chemical equilibrium since a new product is formed. And remember, the rate at which nitrogen and hydrogen form NH3 is equal to the rate at which that NH3 reforms into those. So you can kind of compare 3 different types of equilibrium: phase and solution, which are physical, and then we've got the example of a chemical. Tomorrow we're going to be looking at what happens to a chemical equilibrium when a stress is added to the system. So we'll talk about that tomorrow. Please make sure that you complete the Unit 12, Day 10 skill check. It's pretty short. Use your notes to help you, and I will see you all tomorrow. Bye.